So, we had looked at the disrotatory process, octatetraene going to cyclooctatriene. Now, we are looking at the conrotatory process, and the conrotatory process we require to look at C2 axis of symmetry. Theta 1, theta 2, theta 3, theta 4, theta 5, theta 6, theta 7, theta 8. A, S, A, S, A, S, A, S. This is your sigma, this will be your phi 1, phi 1 is between these two, phi 2, phi 3, phi 4, phi 5, phi 6, sorry, where is it? Phi 1. Theta 1 is less than this, theta 2 is between these two, theta 3 is between these two, theta 4 is here. Theta 4 is less, that is your phi 4, phi 5, phi 6, and this is your sigma star. Okay. So, now A, S, A, S, A, S. Sigma is symmetric with both, this is antisymmetric with both. Theta 1 is antisymmetric, so it goes up. Here in conrotatory 1, 3 and 5 will give you anti-bonding. Okay. So, 2 will go down, 3 is antisymmetric, 4 is symmetric, 5 is antisymmetric, 6 is symmetry, antisymmetry. See this 1, 3, 5, 7 have gone up in energy, 2, 4, 6, 8 have gone down in energy. Thermal reaction, theta 1, 2, theta 2, 2, theta 3, 2, theta 4, 2. Theta 1, 2 has gone into phi 1, 2. Theta 2, 2 has gone into sigma 2. Theta 3, 2 has gone into phi 3, 2. Theta 4, 2 has gone into phi 2, 2. Ground state has given ground state. 8 electrons is an example of a 4q system. Therefore, thermal reaction is convoluted. Theta 1, 2, theta 2, 2, theta 3, 2, theta 4, 1, theta 5, 1. Theta 1, 2 has gone into phi 1, 2. Theta 2, 2 has gone into sigma 2. Theta 3, 2 has gone into phi 3, 2. Theta 4, 1 has gone into phi 2, 1, and theta 5, 1 has gone into 551, equivalent of exciting electron from phi 2 into phi 5. So, first excited state has given very high energy excited state. Therefore, reaction is disallowed. So, without writing orbitals, if I ask you do for 10 electrons, story is the same. This rotatory SA, go on doing this. Okay. All right. Okay. So far, all our species were even number of carbons. Now, we are going to look allyl cation. Going to cyclopropyl cation. Allyl radical going to cyclopropyl radical. Allyl anion going to cyclopropyl anion. Or I can put this whole thing very easily, allyl system going to cyclopropyl system. All right. So, we want to analyze this picture. If I look at this picture now, how many electrons are involved? 2 electrons in the double bond, no electron in positive charge. Therefore, this is a 2 electron system. It is an example of 4q plus 2. Therefore, our rules tell us that this should be thermal reaction, disrotatory, photochemical reaction, conrotatory. When I look at this system, it is a 4 electron system. 4 electron is an example of a 4q system. Therefore, thermal reaction should be conrotatory, photochemical reaction should be disrotatory. But when I look at this system, I have 3 electrons. So, my rules do not tell me what is going to happen. So, my rules do not tell me this. Okay. So, let us look at how we can analyze this system. Okay. What are the orbitals here? The cyclopropyl system, which is the orbital? This is your sigma orbital. Which is your other orbital? Your other orbital is going to be sigma star orbital. And what is your last orbital? Your last orbital is going to be a p orbital. Okay. So, mirror plane symmetry, we know this story, that sigma is symmetric for both, sigma star is anti-symmetric for both. If I show my p orbital like this, This half is minus, this half is minus, this is plus, this is plus. Therefore, your sigma orbital is symmetric for mirror plane. But when I look at C2, what is it? Plus is on top, minus is on top. If you draw orbital through this, I mean mirror plane through this, it is symmetrical. But C2, it is going to be anti-symmetry. Okay. Now, in your allyl system, there are going to be 3 orbitals, x1, x2, x3. X2 is equivalent to a non-bonding orbital, 1 bonding, 1 anti-bonding, 1 non-bonding. So, we must learn how to draw these orbitals. Okay. So, first orbital, that is your x1 orbital. What is the principle? X1 orbital has no node. Therefore, mirror plane symmetric, C2 anti-symmetry. Your third orbital is also very easy, plus, minus, plus. It has 2 nodes, and once again mirror plane is symmetric, C2 is anti-symmetric. Plus, 0, minus. So, it has only 1 node. All right. Mirror plane anti-symmetric, first and last are opposite, therefore, C2 axis is symmetry. So, very easy, very clean picture. Okay. So, that is your x1 orbital, plus, plus, plus. It has mirror plane symmetry. If I do C2, all minus will come there. Okay. Plus, 0, minus. What it mathematically means, do not worry. Anyway, so that is your x2 orbital. Mirror plane anti-symmetric, C2 symmetric. Plus, minus, plus. Mirror plane symmetric, C2 anti-symmetric. Okay. So, once again, what do we see in the open chain system? Mirror plane S A, S A, S A, S A. Even if you do not know how to draw the orbitals, you do this. And for C2, A S, A S, A S. Without knowing how to draw the orbitals, you can do this quite easily. Okay. So, now let us do the picture. Okay. We are looking at the disrotatory picture. We said earlier that FMO is a shortcut picture. Conservation of orbital symmetry is a very rigorous picture. And many times when you take a shortcut in life, sometimes you make a mistake, sometimes it works. So, FMO does not work for this system, but orbital symmetry works. So, that is what we are now going to show. So, this is your allyl system going to cyclopropyl system. Let me put it down. Cyclopropyl system going to allyl system. So, this is your sigma orbital, this is your sigma star orbital, and this is your p orbital. Sigma is bonding, sigma star is anti-bonding, p is non-bonding. X1, X2, X3. All right. Okay. So, what will be the electron picture for this? How many electrons are there? 2 electrons here, no electron here. So, 2 electrons means allyl radical will have X1 2 electrons. Okay, let us put the labels S, A, S, 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 A. So, 2 are symmetric, 1 is anti-symmetric. Joining. Obviously, sigma can join to X1 or X3, I join it to X1. P is symmetric, so I join it here. And sigma star is anti-symmetric. So, that is my correlation diagram. Okay. Now, allyl cation. Thermal reaction. What is the thermal reaction? 2 electrons in X1. Where do these X1 electrons go? Will go into sigma. So, ground state gives ground state. Therefore, as our rules tell us, 2 electron system, the thermal reaction is going to be disrotatory. Okay. When I go to photochemical, what will happen? 1 electron from X1 will go to X2. X1 1 electron, X2 1 electron. X1 1 electron will go into sigma, X2 1 electron will go into sigma star. So, you are exciting electron from sigma into sigma star. So, sigma star. So, first excited state gives high energy excited state. Therefore, disallow. Please, I repeat, if you have a problem, do not keep quiet, ask. Okay. Let us look at our next system, allyl anion. What is the picture in allyl anion? There are 4 electrons, 2 electrons in the double bond, 2 electrons in the negative charge. So, your ground state will be X12, X22. Thermal reaction X12, X22. X1 2 electrons, will go into sigma, x2 2 electrons will go into sigma star. This is ground state, this is not the ground state. Allyl anion is a 4 electron system, and our rule tells us that this rotatory should be not allowed. What will happen in the photochemical reaction? One electron from highest occupied molecular orbital will go to lowest unoccupied molecular orbital. So, we will have x12, x21, x31. Where will x12 electrons go? They will go into sigma, x21 electron will go into sigma star, x31 electron will go into P. So, first excited state has given first excited state. If I look at this, x1 and x3, terminal lobe interaction will give me bonding. So, x1 goes down, x3 goes down, x2 goes up. So, there is no error there. All right. So, what is the HOMO? The HOMO for the thermal reaction of allyl cation is x1. x1 goes down, therefore, it is allowed. HOMO for the photochemical reaction is x2, x2 goes up, therefore, disallowed. What is the picture here? HOMO for this thermal reaction, HOMO is x2, x2 goes up, therefore disallowed. For the photochemical reaction, x3 is HOMO, x3 goes down, therefore it is allowed. Now we look at the allyl radical. When I look at allyl radical, how many electrons there will be in allyl radical? 2 electrons in the double bond and 1 electron in the radical. So, that is going to be your allyl radical picture. So, x1 2 electrons, x2 1 electron. Where does x1 2 electrons go? It goes into sigma. Where does x2 1 electron go? It goes into sigma star. This is ground state, this is not the ground state. Therefore, it is disallowed. When I do photochemical, what will happen? Electron from highest occupied molecular orbital will go to lowest unoccupied molecular orbital. So, x12, x31. Where do these electrons go? x12 electrons come into sigma, x31 electron will go into P. This is first excited state, this is not first excited state, this is the ground state. Therefore, reaction is going to be disallowed. So, whether I do it thermally or I do it photochemically, this rotatory is disallowed. Okay. Let us now draw the picture for the conrotatory process. Okay. A, S, A, S, A, and P is A. So, join them. Sigma is symmetric, there is only one symmetric orbital, so sigma goes here. X1 is, P is anti-symmetric, so it can go here or here. This is lower in energy, so it goes here. So, that is the correlation diagram for the conrotatory process. Allyl cation, thermal reaction. What is the ground state? X1 has 2 electrons. Where does X1 electrons go? It goes into P. Ground state, not ground state. Therefore, disallow. In the conrotatory process, what will happen? When I do this, this will be plus, this plus will go outside. So, 1 and 3 will go down, 2 will go up. Sorry, 1 and 3 will go up, only 2 will come down. All right? Okay. Photochemical, X11, X21. X11 will go into P, X21 will go into sigma. First excited state gives first excited state. Therefore, reaction is allowed. Allyl anion, X12, X22. As we wrote here, no difference. All right. Where does my X12 go? My X12 goes into P, my X22 goes into sigma. Ground state gives ground state. Therefore, reaction is allowed. Photochemical, X12, X21, X31. X12 goes into P, X21 goes into sigma, X31 goes into sigma star. So, first excited state gives high energy excited state. Oh, as the rules predicted, allyl anion conrotatory is allowed. Allyl cation photochemical is allowed. So, rules are followed. Now, you look at allyl radical. In your allyl radical, what is the picture? X12, X21. X12 will go into P, X21 will go into sigma. This is ground state, this is not the ground state. Ground state will have 2 in sigma, 1 in P. Photochemical, X12, X31. X12 will go into P, X31 will go into sigma. First excited state gives very high energy excited state. So, conservation of orbital symmetry tells us that allyl radical, whether I do thermal, whether I do photochemical, this rotatory is not allowed, conrotatory is also not allowed. That is the picture that you see. Let us look at this. Here your HOMO is X1. What happens to X1? Goes up, therefore not allowed. Here HOMO is X2, it goes down, therefore it is allowed. Here again X2 is HOMO, it goes down, therefore allyl anion con is allowed. X3 is there, X3 goes up, therefore it is allowed. Okay. So, what is now the story? If I use FMO, what do I do in FMO? Look at the HOMO. HOMO of allyl cation is X1. What will we say? This rotatory is allowed. This rotatory gives me bonding, therefore allowed. In photochemical, my HOMO is X2. X2 will give me anti-bonding, therefore it will be disallowed. If I do conrotatory, plus will come here, minus will come here, so this will be bonding. So, conrotatory will give me bonding. So, photochemical, this rotatory is allowed, photochemical, conrotatory is allowed. Allyl anion, HOMO for the thermal reaction is X2. X2 with this rotatory, anti-bonding, therefore disallowed. Conrotatory gives you bonding, therefore allowed. Photochemical, one electron from X2 will go to X3. X3, this rotatory will give me bonding, therefore allowed. Conrotatory will give me anti-bonding, therefore disallowed. So, for cation and anion, FMO gives you the same result. But when I look at allyl radical, what is the HOMO of the allyl radical? X2. X2, what did we say 1 minute ago? Conrotatory should give me bonding. So, allyl radical thermal reaction should be conrotatory. But when we look at orbital symmetry, answer is allyl radical does not give this. Okay. Conrotatory should give me bonding, but this is not confirmed by experiment. Experiment tells us allyl radical does not give you concerted reaction. Okay. Photochemical, X3 is HOMO. So, this rotatory should give me bonding, but that also is not observed. So, the shortcut approach does not work for allyl radical, but orbital symmetry approach works very nicely for the allyl radical. Okay. Yes, please.
Sir, what is the meaning of that zero site?
Zero site means these orbitals are not in the same plane as this. Okay. I mean, this which I am telling now is a oversimplification. Okay. What we are saying is this orbital is in a different direction than this. All right. This is your pentadienyl cation. How many electrons? 4 electrons. Therefore, what does our rule tell us? Thermal should be conrotatory. Okay. Pentadienyl anion. What does it have? 6 electrons. Therefore, thermal should be this rotate. And when I look at pentadienyl radical, it has 5 electrons. Our rule tells us nothing. Okay. We are not going to do this, okay? That's for you to do. So, what have we to, how will we tackle this? So, I will show it. Pentadienyl system goes to cyclopentenyl system. What will be the orbitals of this system? This is your allyl system, sigma, sigma star. So, your orbitals will be sigma, x1, x2, x3, sigma star. Therefore, we must know something about what will we do for the pentadienyl system. Here we did x1, x2, x3. So, we will do y1, y2, y3, y4, y5. Two bonding, two anti-bonding, one non-bonding. Just like in allyl, one bonding, one anti-bonding, one non-bonding. Okay. All right. So, what have we to do? Write the orbitals of pentadienyl system. Plus, 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 plus. Zero nodes. So, this is your y1 orbital. It has no node. Mirror plane is symmetric. C2 is antisymmetric. All pluses are on the top. When you turn it, all negatives will be under. Okay. What have I done? There is one node. Where is that node? That node is here. One node. Can you see something? Mirror plane will be antisymmetric. C2 will be symmetric. First and last is opposite, second and second last is opposite. So, this is your y2. y3 plus 0, minus 0, plus. Your non-bonding orbital is always plus 0, minus 0, plus 0, minus 0, plus 0, minus 0. If I ask you to draw 99, you just go on repeating this story, no problem. Okay. What will you see? One node, two nodes. What will we see about symmetry? Mirror plane is symmetric, C2 is antisymmetric. plus minus 0 plus minus. How many nodes? One node, second node, third node. Y4. First and last is opposite, second and second last is opposite. So, symmetry here, anti-symmetry. Last one is always very easy. Just like first is very easy, last is also very easy. Plus, minus, plus, minus, plus. One node, two nodes, three nodes, four nodes. Mirror plane symmetric. Sorry. Wi-Fi, four nodes. What do you see? S, A, S, A, S. Even if you can't write the orbitals, you can draw the picture. Very easy. So, on one side you will draw Y1, Y2, Y3, Y4, Y5. On that side, sigma, X1, X2, X3, sigma star. Draw the picture and make the prediction. Okay. So, the theory is over. Now we are in the practice. All right. So, we look at our first example in the practice. All right. So, let us look at our first example. What is our starting compound? Cyclic with one double bond. Our product is acyclic with two double bonds. So, you are going from one double bond to two double bonds. It is an electrocyclic ring opening reaction. Electrocyclic ring opening reaction. How many electrons are involved? Two electrons and two electrons. So, it is a 4 electron thermal reaction. Therefore, 4 electron thermal reaction is going to be conrotatory. Okay. All right. So, what is it we are doing? What are we saying? Our two metal groups are both on the upper surface. What is the meaning of conrotatory? My thumbs are going to move clockwise. Therefore, what will happen? One methyl group will be inside, one methyl group will be outside. One methyl group is outside, one methyl group is inside. What does this translate into? This double bond is trans, this double bond is cis. What is the next thing we have to understand? In a thermal reaction, you always go from less stable to more stable. Why is this less stable? Because the 4-membered ring, though it has more sigma bonds, it has lot of angle strain. Therefore, 4-membered ring goes to open chain. Okay. sorry, cyclic olefin. From diene, from 2 double bonds you are going to 1 double bond. Therefore, it is again an example of an electrocyclic reaction. Today, all our reactions are going to be electrocyclic, but in the exam, he will not tell you I am an electrocyclic. You have to find out whether reaction is electrocyclic or cycloaddition. Okay? All right. So, you get a cyclic olefin. So, you are going, it is a ring forming, electrocyclic ring forming reaction. Okay. What is the next thing we see? How many electrons are involved? 4 electron photochemical reaction. What does our formula tell us? 4 electron photochemical reaction is going to be disrotatory. How are our 2 metal groups? One metal group is inside, one metal group is outside. Disrotatory means thumbs must move in opposite direction. So, what will happen? Product will have one metal group up, one metal group down. What have we to remember? In a photochemical reaction, stability is not important. You go from more conjugated to less conjugated. Even this compound is more stable than this, but you are going from more conjugated to less conjugated. I heat this and I get a product C, and my C is a acyclic diene. Therefore, I am going from 1 double bond to 2 double bond. Therefore, it is again electrocyclic ring opening reaction. Four electron thermal reaction is going to be conrotatory. So, what is the picture? One metal group is up, one metal group is down. If I move both in clockwise manner, what happens? The 2 methyl groups create problem. So, I move it in the other way. When I move it in the other way, both my metal groups are outside. I can get in principle this, but this will be having much more energy, so it prefers to do the other thing. So, I get into that product. Now, this is trans-trans hexadiene. So, what are the steps? First, you have to decide what is the reaction. So, once we say it is electrocyclic, n pi going to n minus 1 pi is an electrocyclic reaction. Number 2, how many electrons are involved? So, next step you say it is 4 electron reaction. Then you look at this symbol, it is thermal. So, you say 4 electron thermal reaction is conrotatory. Next job is to do this. As I said at the very first time, in the exam also, take your 2 pencils with you, alright. Examiner may think you are stupid, but alright, that does not matter. Because many times after writing everything correctly, in the last step people make a mistake, alright. If you have imagination, you can do it properly. People like me, I prefer to put this, alright. So, that is 4 electron thermal reaction. Our second reaction was 4 electron photochemical reaction. Therefore, it is disrotatory. And our third reaction is again 4 electron, its thermal is conrotatory. What did happen? I started with this cyclobutene, I converted into that cyclobutene. So, 2 methyl cis, 3,4 dimethyl cis converted into 3,4 dimethyl trans. When I start with 3,4 dimethyl cis, my thermal reaction gave me cis trans. When I started with trans, the product gave me trans trans. Okay. Will this product be optically active? No. Why not? It has a plane of symmetry. Will this product be optically active? Is it center of symmetry? No, it does not have center of symmetry. Where is that center? If you say this is the center, then what about this? This hydrogen should have been then here. Okay? So, it should be therefore, it will be optically active or not? Why? Define the absolute configuration at this carbon. 1, 2, 3, 4. What are the substituents? Carbon number 2, carbon number 4, methyl group, hydrogen. So, it is asymmetry. What is the priority order? This carbon is joined to 2 real carbons. This carbon is joined to double bond, which is equal to 1 real and 1 0. Therefore, first, second, third. What is the direction? Clockwise. Hydrogen is below. Therefore, this is R center. Look at this, first, second, third. Direction is, sorry, anti-clockwise, but hydrogen is above. Therefore, it is also R center. Whereas here, one is R center, one is S center. Rotation of R center will be plus X, rotation of S center will be minus X. So, first one will be internally compensated, plus X, minus X, 0. So, what about this? Product will be racemic. Why racemic? When I do the rotation, this methyl group can be above, but also this methyl group can be below. So, I will get equal amounts of compound which have both R and equal amount of compounds which have both S. What is the principle? If my starting material is not optically active and my reagent is not optically active, my product can never be optically active. My product will always be racemic. Okay? So, that is the important picture that we can have. Okay. We had been looking at the approach based on conservation of orbital symmetry. We had first looked at approach based on orbital analysis. Then we looked at the approach based on frontier molecular orbitals, and when we stopped, we had been looking at the approach based on conservation of orbital symmetry. Let us quickly run through the picture. That is your psi 1 orbital, mirror plane, symmetric, C2 antisymmetric, plus plus minus minus, psi 2 orbital, mirror plane, antisymmetric, C2 axis symmetric, your psi 3 orbital, plus minus minus plus, mirror plane symmetric, C2 axis antisymmetric, plus minus plus minus, psi 4 orbital, mirror plane antisymmetric, C2 symmetry. When we look at sigma orbital is symmetric with regard to both your pi orbital is symmetric with regard to mirror plane, antisymmetric with regard to this, and your pi star orbital is antisymmetric for this, symmetric for this, and your sigma star orbital is antisymmetric for both. The second important feature is when we look at this, we are not looking at the symmetry of the molecule, we are looking only at the symmetry of the orbitals. Okay. Then we drew the correlation diagram for the disk rotatory process, and we said that the disk rotatory process is always associated with a mirror plane symmetry. The con rotatory process is associated with a C2 axis of symmetry. And then psi 1 is below this, psi 2 is above this, psi 3 is this, psi 4 is this. Okay. Then we put the labels S, A, S, A, here also S, A, S, A. We joined orbitals of like symmetry, therefore, sigma is joined to psi 1, pi is symmetric, so it can join either to psi 1 or psi 3. Since psi 1 is occupied, we join it to psi 3. Pi star is antisymmetric, we join it here. We join it here because of the principle of minimum crossing. So, we made the correlation diagram for the disk rotatory process. Then if we look at the butadiene, cyclobutene, if we look at the butadiene to cyclobutene reaction, for the thermal reaction, psi 1 2, psi 2 2, psi 1 2 goes into sigma, psi 2 2 goes into pi star. This is ground state, this is not the ground state, therefore, reaction is disallowed. When I look at the photochemical reaction, one electron from psi 2 goes to psi 3. Psi 1 2 electrons goes into sigma, psi 2 1 electron goes into pi star, psi 3 1 electron goes into pi. So, first excited state gives first excited state, therefore, reaction is allowed. And this is what our rule tells us. For the 4Q system, the thermal reaction is conrotatory, the photochemical reaction is disrotatory. And for the 4q plus 2, it's opposite. Okay. Let's look at the cyclobutene to butadiene picture. The ground state will be thermal reaction sigma 2 pi 2. Sigma 2 goes into psi 1, pi 2 goes into psi 3. This is ground state, this is not the ground state. Therefore, it is disallowed. When you look at photochemical reaction, 2 electrons in sigma, 1 in pi, 1 in pi star. Your sigma 2 electrons go into psi 1, your pi electron goes into psi 3 1, your pi star electron goes into psi 2. So, first excited state gives first excited state. Therefore, reaction is allowed. Now, we introduce another concept. Whether we have drawn this correctly, we can look at what is called as the terminal lobe interaction. What does this concept tell us? What is this process? I am moving my thumbs in the opposite direction. When I move my thumbs in opposite direction, what is the result? Plus will go with plus. So, the interaction is bonding. Bonding means psi 1 will go down in energy, psi 3 will also give you bonding interaction. Therefore, psi 3 will also go down in energy. When I do this, what will happen? I will get an anti-bonding interaction. Therefore, when you get anti-bonding, it goes up in energy. Psi 2 goes up, psi 4 goes up. So, it will be a check that you have drawn it in the correct manner. All right. Which is your highest occupied molecular orbital for the thermal reaction? Psi 2 is highest occupied molecular orbital. So, psi 2 goes up, therefore, disallowed. If I look at photochemical reaction, which is the highest occupied molecular orbital? Psi 3. Psi 3 goes down, therefore, reaction is allowed. So, that is the question of the terminal lobe. Now, we are going to draw this. We had done last time, so we went very fast over it. Just recapitulation. Sigma, sigma star, pi, pi star. Psi 1, psi 2, psi 3, psi 4. Since this is the con-rotatory process, the con-rotatory process will be associated with a mirror plane, I am sorry, with the C2 axis of symmetry. So, the labels that we will put will be labels of the C2 axis of symmetry. Even without looking here, A, S, A, S. So, we put the labels of this here also, A and S. Sigma is symmetric to both, sigma star is anti-symmetric to both. Cyclobutene going to butadiene. Sigma is symmetric, therefore, I can join it to psi 1 or psi 4. psi 1 is lower in energy, therefore, principle of minimum crossing tells me that sigma will be joined to psi 1. Pi is anti-symmetric, sorry, sigma is going to join to psi 1. Psi 2 or psi 4, sorry. Sigma is symmetric, psi 2 is symmetric, psi 4 is symmetric, therefore, I can join it to psi 2 or psi 4. Principle of minimum crossing tells us that I should join it to the orbital which is lowest in energy, the orbital which is available and which is lowest in energy. When I look at pi, pi is anti-symmetric, therefore, I can join it to psi 1 or psi 3. Psi 1 is lower in energy, therefore, I join it to psi 1. When I look at pi star is symmetric, therefore, I can join it to psi 2 or psi 4. Psi 2 is already occupied, therefore, I have to join it to psi 4. When I look at my sigma star orbital is anti-symmetric, I can therefore join it to psi 1 or psi 3. Psi 1 is occupied, therefore, I will join it to psi 3. Okay. So, we look at the butadiene to cyclobutene transformation. Thermal reaction, 2 electrons in psi 1, 2 electrons in psi 2, psi 1 electrons go into pi, psi 2 electrons goes into sigma, ground state gives ground state, therefore, reaction is allowed. That is what our rule tells us, that the 4Q reaction, thermal reaction is going to be conrotate. Okay. Let us look at photochemical reaction, psi 1 2, psi 2 1, psi 3 1. Psi 1 2 will go into pi, psi 2 1 will go into sigma, psi 3 1 will go into sigma star. So, this is equivalent of exciting an electron from sigma orbital into sigma star orbital. So, that is a very high energy excited state. First excited state gives high energy excited state. Therefore, photochemical reaction is disallowed. Okay. Let us apply principle of terminal lobe interaction. Now, we are going to make the process conrotatory. So, when I do this in my conrotatory process, plus will go here, plus will go here. So, this will be minus. So, psi 1 will give me anti-bonding, therefore, psi 1 goes up in energy. Similarly, psi 3 will also give me anti-bonding, therefore, psi 3 also goes up in energy. By contrast, psi 2 plus will go here, minus will go here. So, plus will be here, minus will be here, therefore, this will be plus. So, psi 2 and psi 4 will give me bonding. So, psi 4 comes down, psi 2 comes down. So, that is the picture. Okay. Let us look at that shortcut approach. What is the shortcut approach? In this approach, thermal reaction, HOMO is going to be psi 2. psi 2 goes down, therefore, reaction is allowed. In photochemical reaction, HOMO is going to be psi 3. Psi 3 goes up, therefore, reaction is disallowed. Okay. So, we now look at the cyclobutene to butadiene. Where will these electrons go? Your thermal reaction, 2 electrons in sigma, 2 electrons in pi. Miss, where will the sigma electrons go? Sigma electrons will go psi 2. Sigma electrons will go into psi 2. Your pi electrons will go psi 1. Ground state has given ground state, therefore, reaction is allowed. We look at photochemical, 2 in sigma, 1 in pi, 1 in pi star. Where will these electrons go? Miss, where will these electrons go? Sigma 2 electrons will go into psi 2. Pi 1 electron will go into psi 1. And pi star 1 electron will go into psi 4. It is exciting psi 1 electron into psi 4. So, it is a high energy excited state. First excited state is high energy excited state. Therefore, reaction is disallowed. What is the ground state? HOMO for the thermal reaction is pi. Pi is going down, therefore, reaction is allowed. In the photochemical reaction, HOMO is going to be pi star and pi star is going up, therefore, disallowed. If you will see the answers that we got from orbital symmetry and the answers that we got from orbital analysis, correlation diagram exactly the same, end results exactly the same. Okay. So, we are now going to look at our next example. We are considering now that is your hexatriene, and hexatriene is going to cyclohexadiene. Okay. When I look at hexatriene, what are going to be my orbitals? The 6 orbitals are going to be the 6 orbitals of hexatriene. And for this part, we will have 4 orbitals of butadiene and sigma orbital and sigma star orbital. So, that is your sigma star orbital, which is anti-symmetric with regard to both. Okay. So, what are my hexatriene orbitals? That is my hexatriene orbitals. That is your phi 1 orbital. What do I see? Mirror plane, it is going to be symmetry. C2 axis, first and last are not opposite, therefore, C2 axis is going to be anti-symmetry. Your phi 2 orbital must have one node. So, 3 positives, 3 negatives, that is going to be your node. What can we see from this? Mirror plane is obviously anti-symmetric. C2 axis, first and last is opposite, second and second last is opposite, third and third last is opposite. Therefore, it is symmetric for C2 axis. What is this? This is your HOMO, plus plus, minus minus, plus plus. How many nodes? One node here, one node here. What is it for mirror plane? Mirror plane is going to be symmetric. C2, first and last are not opposite, so it is anti-symmetry. How do I draw LUMO? Plus, minus, minus, plus, plus, minus. Your phi 4 orbital, one node, second node, third node, 3 nodes, therefore, this is the 4th orbital. Mirror plane is anti-symmetric. C2, first and last is opposite, second and second last is opposite, third and third last is opposite. Therefore, C2 is going to be symmetric. Plus, minus, plus, plus, minus, plus. One node, second node, third node, fourth node. This is your 5th orbital. Mirror plane is symmetric, C2 is anti-symmetric. And your last orbital, plus, minus, plus, minus, plus, minus. One node, 2 nodes, 3 nodes, 4 nodes, 5 nodes. Your 6th orbital, mirror plane anti-symmetric, C2 symmetric. First and last is opposite, second and second last is opposite, third and third last is opposite. Even without doing this, see the point I made last time. Mirror plane, start with S and S, A, S, A, S, A. And C2, start with A, S, A, S, A, S. Okay. All right. I am sure everybody can see this. This is your plus, 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 and that is mirror plane symmetric. When I turn it, all negatives come on the top. That is not going to be satisfactory. Okay. Plus, 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 minus, minus, minus. Mirror plane antisymmetric. C2 we started with a plus, 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 minus, minus, minus. Okay. So, that is the picture. That is your third orbital, plus, plus, minus, minus, plus, plus. Mirror plane is symmetric. C2 is started with minus. So, that is unsymmetry. Okay. Plus, minus, minus, plus, plus, minus. Mirror plane, antisymmetry. C2, first and last is opposite, second and second last is opposite, third and third last is opposite. So, plus, minus, minus, plus, plus, minus. So, that is the picture which is giving you, all right, let us finish it. Plus, minus, plus, which we are drawing plus. Plus, minus, plus, plus, minus, plus. One node, second node, third node, fourth node. Mirror plane is of course going to be symmetry. That is your last orbital, plus, minus, plus, minus, plus, minus. One node, second node, third node, fourth node, fifth node. Mirror plane is obviously antisymmetric. First and last is opposite, second and second last is opposite, third and third last is opposite. So, we started with a plus, we again ended up with a plus. Okay. Psi 1, psi 2, psi 3, psi 4. Okay. Disrotatory, therefore, mirror plane symmetry. Psi 1 S A S A. Sigma is symmetric for both, this is anti-symmetric. All right. Let us put it. Phi 1 is less than psi 1. phi 2 will be between these two. So, phi 1 is below psi 1, phi 2 is between psi 1 and psi 2, phi 3 is above psi 2. Okay. Let us phi 4 is below, phi 5 is in between, phi 6 is here. So, S, A, S, A, S, A. Join this. Where will I join sigma? Sigma will join to phi 1, phi 3 or phi 5. Phi 3 is the one that is lowest in energy. Therefore, I join it to 5. Psi 1 is symmetric. So, once again it can join to orbital number 1, orbital number 3, orbital number 5, phi 1, phi 3, phi 5. Phi 1 is occupied. Of the two, phi 3 is lower in energy. Therefore, I will join it to phi 3. Okay. Then we look at psi 2. Psi 2 is anti-symmetric. Therefore, it can join to 2, 4 or 6. 2 is the one of lowest energy. So, I will join it to 2. Psi 3 is symmetric. Therefore, it can join to 1, 3 or 5. 1 and 3 are occupied. Therefore, I must join it to 5. Psi 4 is anti-symmetric. Therefore, it can join to 2, 4 or 6. 2 is occupied. Therefore, I must join it to 4. Sorry, what did I do? Psi 2, psi 4, what, sorry, psi 2 is joined to this, psi 4 is joined to this, and sigma star is anti-symmetric, so I can join to 2, 4 or 6. 2 and 4 are occupied, so I must join it to this. While making correlation diagram, important feature is, since it is disrotatory, I must use mirror plane labels. Okay. All right. Now, let us look at the terminal lobe interaction. Disrotatory, plus and plus moving in this direction will give me bonding. So, 1, 3 and 5 will give me bonding. Sorry. Okay. 1, 3 and 5 will give me bonding. So, 1, 3 and 5 go down in energy. 2, 4 and 6 will give me anti-bonding. Therefore, they will go up in energy. So, 2, 4 and 6 go up in energy. Therefore, what the picture we have drawn is all right. Okay. So, that is the check we have made. Okay. So, let us look at hexatriene going to cyclohexatriene. Let us also see one thing. When I look at butadiene UV, I am exciting, I need so much energy. When I look at hexatriene, I need much less energy. Therefore, butadiene absorbs at 217, hexatriene absorbs at 254. Okay. So, 512, 522, 512, 522, 532. Yes, please. Where do these electrons go? 512 goes into sigma, 522 goes into psi 2, and 532 goes into psi 1. Ground state gives ground state. Therefore, this is an example of 4Q plus 2. So, 4Q plus 2, the thermally allowed reaction is disrotate. Okay. Let us look at the photochemical reaction. 512, 522, 531, 541. 512 goes into sigma, 522 goes into psi 2. 531 goes into psi 11, and 541 goes into psi 41. It is equivalent to exciting an electron from psi 1 to psi 4. Therefore, it is a high energy excited state. First excited state gives high energy excited state. Therefore, photochemical reaction is disallowed. Okay. Let us look at it shortcut approach. What is the shortcut approach? Look at phi 3. Your HOMO is phi 3. Where does phi 3 go? Phi 3 goes down. Therefore, allowed. In your photochemical, your HOMO is going to be phi 4. Where does your phi 4 go? Your phi 4 goes up. Therefore, it is disallowed. Even without making the full diagram, what do we say? 1, 3 and 5 in disrotatory come down, 2, 4, 6 go up. When the HOMO is 3, it is going down, therefore, reaction is allowed. In photochemical, your HOMO is 4, 4 is going up, therefore, reaction is disallowed. Okay. Let us look at the back reaction. Your back reaction, cyclohexadiene going to hexatriene. Sigma 2, psi 1 2, psi 2 2. Miss, where do these electrons go? Sigma 2, phi 1, 2 electrons. Where does your psi 1 electron go? Psi 1 electron, phi 3. It is not enough to say phi 3, you must put the number of electrons. Where does your psi 2 electrons go? Yours goes into phi 2. And how many electrons? 2 electrons. Ground state gives ground state. When I do photochemical, what will happen? An electron from psi 2 will go into this sigma 2, psi 1 2, psi 2 1, psi 3 1. Next person please, where does sigma go? Don't say only 5, phi 1, 2 electrons. Psi 1, 2 electrons go into phi 3, 2 electrons. Psi 2, 1 electron goes into phi 2, 1 electron. And psi 3, 1 electron goes into phi 5, 1 electron. Equivalent of exciting electron from phi 1 into phi 5. So, first excited state gives high energy excited state. Therefore, reaction is disallowed. Everybody is all right? Okay. So, we are now looking at the con-rotatory process. And the con-rotatory process should be associated with a C2 axis of symmetry. Sigma psi 1, psi 2, psi 3, psi 4, sigma star. A, S, A, S. This is symmetric for both, this is anti-symmetric for both. Phi 1 is lower in energy than psi 1, phi 2 is in between, phi 3 is here, phi 4 is lower than this, phi 5 is in between, phi 6 is here. A, S, A, S, A, S. Yes, please. Where do I join? Where do I join this? Sigma. Sigma is symmetric. Therefore, sigma can go to phi 2, phi 4, phi 6. Phi 2, phi 4, phi 6. Phi 2 is lowest in energy. Therefore, I join it here. Psi 1 is anti-symmetric. Therefore, it will go to phi 1, phi 3, phi 5. Phi 1 is lowest in energy, therefore, I go to this. Psi 2 is symmetric, therefore, it can go to 2, 4 or 6. 2 is occupied, so I join it to 4. Psi 3 is anti-symmetric, so it can go to 1, 3 or 5. 1 is already occupied, therefore, I join it to 3. When I go to psi 4 is symmetric, therefore, it can go to 2, 4 or 6. 2 and 4 are occupied, therefore, I have to join it to 6. Sigma star is anti-symmetric, therefore, it can go to 1, 3 or 5. 1 and 3 are occupied, therefore, I join it to this. what do I see when I make the disrotatory process, I am sorry, conrotatory process? Plus will go here, plus will go outside. Therefore, it will give me anti-bonding. Therefore, 1, 3 and 5 will go down, sorry, 1, 3 and 5 will go upwards, and 2, 4 and 6 will go downwards. So, 2, 4 and 6 go downwards. So, our picture, we have made no mistake in joining. Okay. 512, 522, 532. This is your thermal reaction. 1, 2, 3. Yes, please. Where do these electrons go? 512, 512 goes into psi 12. 522 goes into sigma 2. 532 goes into psi 32. Ground state, this is not the ground state. Therefore, reaction is disallowed. Photochemical reaction. 512, 522, 531, 541. Five 1 2 goes into psi 1. 522 goes into sigma. 531 goes into psi 3, and 541 goes into psi 2, equivalent of making psi 2 into psi 3. So, first excited state has given first excited state. Therefore, 6 electrons photochemical reaction is allowed. Okay. Once again, what can we say? HOMO for the thermal reaction is phi 3. Phi 3 goes up, therefore is disallowed. For the photochemical reaction, HOMO is phi 4. Phi 4 comes down, therefore is allowed. Here, HOMO is phi 4, phi 4 goes down, therefore allowed. Okay. Let's do it for the reverse reaction. The cyclohexadiene to hexatriene. Sigma 2, psi 1 2, psi 2 2. Sigma 2 goes into phi 2 2. Psi 1 2 goes into phi 1 2. And psi 2 2 goes into phi 4. Ground state, this is not the ground state, therefore disallowed. HOMO for this is psi 2. Psi 2 goes up, therefore disallowed. Photochemical, sigma 2, psi 1 2, psi 2 1, psi 3 1. Sigma 2 goes into phi 2. Psi 1 2 goes into phi 1 2. Psi 2 1 goes into phi 4 1, and psi 3 1 goes into phi 3 1. First excited state gives first excited. What is your HOMO? Your HOMO is psi 3. Psi 3 goes down, therefore, reaction is allowed. So, we can see that once you follow certain principles, everything becomes relatively easy. Please remember once again, when we talk of symmetry, it is only symmetry of the orbitals. If I put a methyl group, nothing will change. Though symmetry of molecule will change, but we are looking only at symmetry of the orbitals. Okay. Octatetraene going to cyclooctatriene. Okay. So, what will be the orbitals here? Theta 1 to theta 8. 8 orbitals will be theta 1 to theta 8. And what will be the orbitals here? 6 orbitals will be hexatriene and sigma star. Okay. Phi 1 to phi 6, sigma and sigma star. Now we are increasing the energy in this direction. Okay. So, what will we write? This is your sigma orbital. Phi 1, phi 2, phi 3. These will be your 4 bonding orbitals. Phi 4, phi 5, phi 6, sigma star. Put the labels. We are looking at disrotatory, so mirror plane. So, for this S, A, S, S, A, S, A. The olefinic component disrotatory S, A, S, A, S, A. Sigma is symmetric, this is antisymmetric. Now you put the 8 orbitals. Theta 1 will be here, theta 2 will be between these two, theta 3 will be between these two, theta 4 will be here, sorry, theta 4, theta 5 will be here, theta 6 will be here, theta 7 will be here, theta 8 will be here. symmetric label S A S A S A S A. Join them. So this will join to this. Why? Symmetric will join to this. This is symmetric, therefore it will join to number 3. This is anti-symmetric, so it will join here. Theta 3 is symmetric, therefore it will join to symmetric. Phi 4 is anti-symmetric, so it will join here. Phi 5 is symmetric, so it will join here. Phi 6 is anti-symmetric, so it will join here. All right. We will look only at phi 1 2, phi 2 2, phi 3 2, phi 4 2. Phi 1 2 goes into sigma. Phi 2 2 goes into, what did we write? We should make this theta 1, sorry. Theta 1, theta 2, theta 3, theta 4. Okay. So, theta 2 will go into phi 2. Theta 3 will go into phi 1. And theta 4 will go into phi 4. Ground state, this is not the ground state, therefore, this rotatory is disallowed. Theta 1 2, theta 2 2, theta 3 2, theta 4 1, theta 5 1. Okay. Theta 1, theta 2. Okay. So, theta 1 2 will go into sigma. Theta 2 will go into phi 2. Theta 3 2 will go into phi 1. Theta 4 1 will go into phi 4. And theta phi 1 will go into phi 3. First excited state has given first excited state. What will we see? 1, 3, 5, 7 will go, give you bonding. So, they will go down in energy. 2, 4, 6, 8 will go up in energy. Okay, we will have a little break, then we will come back.